Okay, so good morning. We're going to learn about the concept of the derivative today. This is a pretty big idea. If you watched the earlier video, you learned that differential calculus is one of the these things that we're going to study, so this is a pretty major thing that we're going to learn about here today. I'm also thinking I'm going to be able to teach this to you before Mr. McManus teaches you those of you that are in physics too. Which I rarely get to do that, so I'm kind of pumped about that, actually. So if we're corresponding to like what's in the book, this is section 3.1 is where they introduce this, so that's how we'll organize it for you. But let's just jump in here. So let's go back to Mrs. Bowser's marbles problem. So if we were to think about Mrs. Bowser's marble in the jar situation, let's say that we're making a graph here, and that this function here represented the number of marbles in the total number of marbles in the jar, and this axis here represented days. That's D-A-Y, not D-Y. Okay, and so now we kind of talked about this, that truthfully, this probably wouldn't be a continuous situation. She doesn't have a machine that's constantly pumping out marbles, but this is a nice context for us to think about that's just maybe different than the traditional context. So just imagine she's got this marble machine that's pumping out marbles, and it looks like the class is behaving pretty well. This is similar to the first graph that we looked at. So what I'm interested in here, ultimately, is let's say that this is a particular day of the year, and that day 2. Okay, what I'm really interested in right there on day 2 is how fast are they gaining marbles at that instant, at day 2. Like if there was a marbleometer, like if she had a little gauge that was like a running clock in her room that tells you how fast the marbles are churning out, what would that gauge read right on day 2? So that's what we're kind of interested in finding out. So let's figure out a way that we can do this. So what we're going to do is, I don't know what that number is right now, but if I did this, and I said, well, okay, let's find how fast they went up between day 2 and day 3. Well, that could be indicated, and if this were a regular class, I would ask you, how would this be indicated on this graph? How might you draw that? But since this isn't a class, it's just me yapping at you through a glass wall. Way we're going to indicate that is the rate of change of marbles in that 1 day period could be indicated by the slope of that line right there. We call that a secant line. So I think, if we called this function f, which I'm sorry I didn't name him f. Hello, f. Okay, if we called that function f, the slope of that secant line would just be f of 3 minus f of 2 over 3 minus 2. We'll call that the slope, m for slope, and I'll use SEC for secant. Okay? I think that should make sense to us. Like, yeah, we that's what we did in Algebra 1, we found that slope of that secant line. Sometimes you might hear this referred to as the average rate of change of f between 2 and 3. You'll hear that also. But that isn't answering the question that I was asking. I mean, I want to know how fast is the marbleometer going to say we're pumping out marbles at 2. Not how much did we average between 2 and 3. I want to know what it was at 2. Now, I think most of us could say, hey, well, this is a ballpark. I mean, this is a kind of an idea of how fast it was going. I think we could maybe make it better. How could we make it better? Well, what if we, instead of using 2 and 3, what if we picked another value that was maybe a little closer to 2? Like maybe, say, 2.5. And we found the slope of that line. Okay? How would we, what would be represented, or how would we represent that slope? Well, algebraically, we would say that's f of 2.5 minus f of 2 over 2.5 minus 2, right? That's a different line, a different secant line. It's a different average rate of change, but it's maybe closer to the answer that I was looking for of what's the marbleometer reading right there. In fact, some of you may realize from previous work or Mr. McManus's class that the slope that I'm really after is that slope right there, which is the tangent line slope. That's really the slope that we're after. What's the slope of that tangent line? You know, in Algebra 1, you learned you need 2 points to find the slope of a line. That's what you learn. But pretty soon we're going to learn that you really don't. Okay, so, you know, yes, this second slope is closer to the slope of that tangent line, that pink slope, but how could we make it better? So hopefully you're saying to yourself, hey, I think you can make that better by picking a number that's closer to 2. What if I pick 2.1? You know, that's going to, I mean, my graph is going to get ridiculously complicated here, but just algebraically, that would look like f of 2.1 minus f of 2 over 2.1 minus 2, right? But still, that's not quite there. It's closer to what the slope of that pink line is, but it's still not exactly the slope of that pink line. I mean, what we really need to happen here is we really need the distance between these 2 points to get really, really close to 0, but not necessarily equal 0, because then if the distance between the 2 points equals 0, we wouldn't have 2 points. But we need the distance between the 2 points that we're using to calculate that slope to approach 0, but not necessarily equal 0. I feel like we've heard that language somewhere before. Hopefully you're sitting there thinking, oh yeah, that's a limit. So how do we do this with a limiting process? How do we make this happen with a limit? So really what we have to do is make this horizontal distance between the 2 points that we're choosing to calculate that slope equal 0. So I'm going to show you how we do that, but I do want to point out one thing here, that these numbers here are, the units would all have marbles per day. Okay, so all of these would have units of marbles per day. All right. So again, we need to make this horizontal distance approach 0, but not necessarily equal 0. How are we going to do that? And it's with the idea of limits. So there are really 2 ways that we're going to algebraically package this idea. And so that's what I'm going to show you right now, is how we package that idea algebraically. So it's going to involve a new picture. So I'm going to pause this while I erase. Okay, so we're back. I had to erase the board, and then I think someone came in my room, so I had to figure out what they wanted. But we're back. So what we're trying to do here is we're going to algebraically package this idea of making that horizontal distance go to 0. So I'm going to redraw a picture here. It's going to be almost the same picture that I just drew. Okay, and I'm going to just make this general. Instead of saying this was x equals 2, I'm just going to say it's x equals a, whatever we want, okay? So I'm interested in this slope right there, the slope of that tangent line right there, okay? And so what are we going to do? Well, just like we did a second ago, I'm going to pick another point down here. And I'm just going to say that's just some arbitrary x value. All right? And so I'm going to put that point up there, and I'm going to say, okay, well, what would be the slope of that secant? What would be the average rate of change between those 2 points? And we would say, well, I know that. That's f of x minus f of a over x minus a. That's the slope of that secant line there. All right, now we said, okay, we need to make this distance between here and here approach 0, but not necessarily equal 0, because if that distance equaled 0, then we would be dividing by 0 here. Okay, and then everything would fall apart, and the world would explode. Okay? How can we make this distance approach 0 but not necessarily equal 0? Well, basically, x has to approach a, but it can't equal a. Okay? So how do we make x approach a but not necessarily equal a? And that's with a limit. Okay? So this expression right here, the limit as x goes to a of f of x minus f of a over x minus a, this is our first way of algebraically packaging this idea. What is this? We refer to that as f prime of a. Okay, so let's talk about all the different ways of representing, or not representing, naming this quantity here. What we just found. It's the slope of the tangent line to f at x equals a. Okay? It's the slope of that pink line there. Okay? It's the slope of the tangent line to f at x equals a. Okay? And we read that f prime of a. That's how we read that. F prime of a. It's what we call the derivative of f at x equals a. Okay? That's another way that we describe that quantity. It's the derivative of f at x equals a. Let's see. Slope of the tangent. It's the derivative of f at x equals a. Sometimes you'll see it written like this. It's dy dx when x equals a. I'm just listing out different ways of explaining or representing that quantity, the answer to this limit, whatever it is. I think another one that we missed, maybe should have said it right at the beginning, it's the instantaneous rate of change of f at x equals a. Okay? Instead of the average rate of change, it's the instantaneous rate of change. It's what the marbleometer would read. If there was a little gauge that told you like how fast the marbles were coming out at any instant, it's what the marbleometer would read at the instant, x equals a. Let's see. Instantaneous rate of change, dy dx. I think we got most of them here. But one thing that I want to point out to you is if you notice something about this little list here, every single one of these all of them say at x equals a. This is what we refer to as the derivative at a point. Okay? So the derivative at a point. It's the instantaneous rate of change. This equation, by the way, is what your book refers to as equation 3.5. We'll talk about that in a second. But like I said, there are two ways to algebraically package this idea. Here's the first way, which they're calling equation 3.5, which is this. I'm going to show you the second way. We're not going to go through this list of terms again because I don't think we need to. They're going to be the same. I'm just going to show you another way to package this idea algebraically. So I'm going to pause this and erase the board because erasing takes time, and you don't need to sit and watch me erase. Okay, so now we're going to talk about that other way to algebraically package this idea of the derivative at a point. I'm going to draw another picture. It's going to be the same picture. Okay. Here's x equals a, so we're interested in, again, that slope of the tangent. Uh-oh, missed that as tangent. You guys probably can't see that on the video. If I make that dot nice and fat, you won't be able to tell. So we're trying to find the slope of that tangent, and we just did it a second ago. We packaged that limiting process one way. Here's another way to package it. So I'm at x equals a. Last time I just chose another arbitrary x down here. I'm going to choose a point down here. Instead of calling that a, I'm going to say, instead of calling that x, I'm going to say that this point right here is a plus h. It's some point further down the road that's h units away from A. So I put another dot here. And so the process is the same, but if you notice here, this part looks a little different. The slope of that secant line, or the average rate of change of f between A and A plus h, is going to look like this. F of A plus h minus f of A over A plus h minus A, which A plus h minus A, I guess we could probably just call that h. Okay? So that's the slope of the green line, the secant line. Now, again, we need to make this distance approach 0, but not necessarily equal 0. So then we're going to get that secant line will become that tangent line for us. So how do we make that happen? The limiting process, we still do a limit, but if you notice this time, what has to approach 0? Before, the way we made that distance go to 0 is we said let x go to A. Now I'm going to say what needs to happen here? H, that distance, h, has to go to 0. Okay? So this is the other way to algebraically package the derivative at a point. This is what the book refers to, by the way, as equation 3.6. I could care less what the book refers to. I care that you understand that this equation here that we just wrote down and the one that we just had before is 3.5, that you understand that those are two different ways of saying the same thing. It's just packaging it a little bit different algebraically. So again, we have the limiting process, we have this horizontal distance going to 0, and we have the value of that slope of the tangent line, or the derivative. So I'm going to erase the board here, and then we're going to do a couple of examples so that you can see what this looks like in practice. Okay, so we're back. Who would have thought that erasing the board takes so much time? So this is actually a good way to save some time. So I've got this function here. This is going to be our example. It's a simple parabola. F of x is 2x squared plus 3x plus 4. And what we're going to do is we're going to find f prime of 3. And then we're also going to go ahead and find the equation of the tangent line to f at x equals 3. Okay, so we're going to do those two things. It turns out, hopefully you realize that in order to do the second thing, you have to do the first thing. Let's get started. We're going to use, in order to do this, what the book calls equation 3.5, that first way that I showed you to calculate the derivative. Actually, before I do this, got to have a little bit of a disclaimer or statement. Some of you may know how to do this using some shortcuts. I'm going to call Mr. McManus this afternoon and ask him if he's already taught some of the physics kids how to do this using the shortcuts. But you can't do it using the shortcuts just yet. You can check your answer with a shortcut, but I need you to go through this limiting process to do the shortcuts. There'll be plenty of time for shortcuts. Don't you worry. So we're going to say that f prime of 3 is equal to the limit as x goes to 3 of f of x minus f of 3 over x minus 3. I realize here now, I see that you can't see this right here at the top, so I'm going to read to you what that says. That just says limit as x goes to 3 right there, f of x minus f of 3, and then over x minus 3. All right, so now we're going to compute this limit. So if you notice, I'm not going to use the equal sign here. This is still equaling f prime of 3. F of x is 2x squared plus 3x plus 4 minus f of 3. Okay, so in order to figure out, or put, what goes here, I got to figure out what f of 3 is. So let's go ahead and do f of 3. So we're going to compute this. Now, if this was a more complex function, you probably would throw it into a calculator and get the value for this function. I think we could probably do this in our head. So let's do 3 squared is 9, times 2 is 18, 3 times 3 is 9, plus 4, So 9 plus 18 plus 9 is 27, plus 4 is 31. Check me on that. Let's see, 13. Yeah, I think so. All right. So now I'm going to say minus 31 right here. And then over x minus 3. Okay, so now before we continue, this problem that we're looking at now is really like a problem that you would have had on homework 2 nights ago. You know, can you compute this by substitution? It turns out you can. If you plug 3 in here, you're going to get 0 over 0. That ain't going to work. So we're going to do this algebraically like we did the other day. So I'm going to step over here so you can see better. So that's going to be the limit as x goes to 3. Now we're going to do some arithmetic here. 2x squared plus 3x. 4 minus 31. 4 minus 31 is minus 27. And now we're going to say, okay, well, I'm going to have to factor this numerator. This is about as complex algebra as complex factoring that we're going to have to do, probably. So 2x. Now, I'm just going to go out on a limb and guess that x minus 3 is going to be a factor of this, because I've done thousands of these. And if you do this correctly, it will be. So now, what am I going to put here that multiplies together to give you 27? I think that would be a 9. You can double check that. 2x times, that's going to negative 6x, plus 9x would be 3x. So that works out. So here we go. So now this is the limit. I'm going to move out of the way so you can see the limit as x goes to 3 of 2x plus 9. And so now we can go ahead and compute that limit by substitution and say that's 2 times 3 is 6, plus 9 is 15. Okay? So what is 15? By golly, don't ever do these problems, or don't do any problems in here or in any math class, and get this answer and not think about, okay, what does this mean? What did we do all this for? Okay? This right here, this 15, is the answer to f prime of 3. It's the slope of this tangent line that we were asking about over here. So now that we know that slope, we can find the equation of that tangent line, because in order to find the equation of a line, any line, you need a point and a slope. And if you remember, what did we say a couple days ago or a couple weeks ago? Calculus is all about point slope. So here's our slope. Here's our point. Now the point is kind of buried right here. It's the point 331. And so we're just going to write our equation of our tangent line. Ready? Y equals 31 plus 15 times x minus 3. Okay? Y equals 31 plus 15 times x minus 3. If you remember, I said in the first video that I made about the big picture of calculus, it's all about point slope. I prefer to write my point slope equations like this instead of y minus 31 equals 15 times x minus 3. I think this tells more of the story. And honestly, just leave your equation like that. There's no reason to put that in slope-intercept form, like y equals mx plus b. In fact, I think this equation tells more of the story than slope-intercept form, because this tells me right now at x equals 3, I'm sitting at 31, and I'm changing that fast. Okay? Tells me the story. So that's that example. So we found f prime of 3 using equation 3.5. And we did that limiting process, did the algebra here, got f prime of 3 is 15, and then we used point slope form to find that equation of the line. In a second, I'm going to erase the board here, and we're going to do another example just using the other algebraic technique, so you can see that. So give me one sec. Okay, so our next example, we're going to use the other technique, which the book calls equation 3.6. And honestly, you probably need to just be comfortable with both of these. So I'm going to give you a new function here. Let's say it's 1 over x plus 2. Okay? And I'm going to change the directions a little bit just so you can get comfortable. I'm going to say find f prime of a. And we're going to say where a is equal to 1. Okay? So basically we're just saying, hey, find the derivative of this function at x equals 1. That's all we're saying. Okay? I noticed that this color matches my shirt today. Maybe you can't see the pink of my shirt because I'm kind of washed out by the light, but whatever. Sometimes I just have random thoughts, you know? So here we go. We're going to use this other technique, which the book calls equation 3.6. So I'm going to start up here, and I'm going to say, well, this is going to be, we'll say f prime of 1 is going to equal the limit as h goes to 0 of f of 1 plus h minus f of 1 over, you guys can't see that. So I'm going to rewrite this again because it's a lot to read again out loud. Let's drop it down. We're going to say that f prime of 1 equals the limit as h goes to 0 of f of 1 plus h minus f of 1 over h. Okay? Now, with this particular problem is going to be a little bit tougher algebraically than the last one. Not because this technique is tougher algebraically, probably because this function is going to be a little bit tougher to work with algebraically. But I don't want you to run away from this technique just because this particular problem happened to be tougher algebraically. It's just as valuable. Okay, so here we go. We're going to go ahead and compute this. But first we got to figure out what all this stuff here is. F of 1 plus h, that's going to be 1 over 1 plus h plus 2. What does f of 1 plus h mean? It means if this is f, take 1 plus h and f it. That's what it means. So we f'd 1 plus h, and that's what it looks like, unsimplified. What does f of 1 mean? That means take 1 and f it. Well, f of 1 is just 1/3. And then this is still all over h. So you can now see that the algebra here is going to be kind of uglier than it was a minute ago. Just, you got these fractions inside fractions and kind of yucky. I'm going to switch colors here just because this blending into my shirt might get a little cray. That should be a 0 there. So we're still looking at the limit as h goes to 0. I'm going to go ahead and simplify the numerator here to 1 over h plus 3 minus 1 over 3 over h. Okay? So now I need to do this algebraically. I got to do the algebra here. I can't just plug in 0 for h because I'm going to get 0 over 0. So I've got to do some algebra. And the algebra that I'm going to have to do is I'm going to have to find a common denominator in the numerator. Find a common denominator in the numerator. So let's do it. So the common denominator, this guy needs a 3 over 3, this guy needs an h plus, if I write them right here, 3 over 3, and this guy needs an h plus 3 over h plus 3. So after I do that, I'm going to get 3 over 3 times h plus 3 minus h plus 3 over 3 times h plus 3. And remember, friends, that was still all over h. So now, I'm going to add those two fractions in the numerator together. The limit as h goes to 0. 3 minus h minus 3 is going to just be minus h in the numerator over 3 times h plus 3 over h. Okay, so that's how the numerator simplifies after you add those two fractions together. And we're still all over h. Don't forget about that. And now, I'm going to go over here, because I'm running out of room down here. And if I simplify this, the h's are going to cancel. because when I multiply by the reciprocal, I'm going to have h in the denominator. So I'm going to have the limit as h goes to 0 of -1 over 3 times h plus 3. Okay, so those h's there canceled. And guys, if you do this right, just on the last problem that we did, where those factors of x minus 3 and x minus 3 canceled, if you do this right, those h's are going to cancel. You're always going to be able to get that h and cancel it with the denominator. It'll happen every time. If it doesn't, then you did some algebra wrong. So now I look at this and I say, okay, well, what is the limit here as h goes to 0? Can I do this by substitution? Because, I'm not going to get 0 over 0 or anything, and it sure is I can. Look, if h goes to 0, I'm just left with -1 over 3 times 3, which is 9. Okay, so what is that -1/9? What does it mean? It is the slope of the tangent to this graph at x equals 1. And if you want the equation of that line, you have the slope, you need the point. The point is going to be, not 3, stupid. Me, stupid, not you. The point is going to be 1 comma f of 1, and we found f of 1 right there. It was 1/3. So if you want the equation of that line, you could say the equation of that line is y equals 1/3 plus -1/9 times x minus 1. Okay? And I actually go ahead, I challenge you, go ahead and open up Desmos, graph this function, and then graph this line. You will see that this line touches this function at x equals 1 and is perfectly tangent. Or look at the last problem and graph that parabola, and then graph the line that we came up with. You'll see that that line is tangent to that parabola at x equals 3. So those are the two examples that these are the types of problems that I'm going to have you do tonight. You're calculating the derivative at a point, finding slopes of tangents, finding instantaneous rates of change, finding dy dx at x equals whatever, the derivative at a point. So here are the problems I'm going to have you look at. It's section 3.1, 11 through 18. Now I'm going to change the directions from the book. Okay, just to give you some practice, on the evens of these, I want you to use what we called, or the book calls, equation 3.5, the first way we did that last one. And the odds, I want you to use equation 3.6. So you've got about seven or eight derivatives to calculate there, and some of them you're going to do using this technique, and then some of them you're going to do using the technique that we did before. So that's all. And make sure you spend some time doing this, because this is good practice. And we'll see you soon.